I want to talk about third module, which is chapter 4 of the of the textbook, Carver and Thomas. And this module also talks about chapter 5, data compression. Okay. So entropy rates of a stochastic process. Shannon has used stochastic process to represent English source. So English source here means typewriter or word processor, starting from left to the right. If you move, basically each alphabet letter occurs. And Shannon has modeled this process as a random process. And he talks about, he introduced the so-called entropy rates to measure the amount of information a English source generates. So that's the subject that Shannon has brought into the picture, which is discussed in chapter 4 and also in Shannon's 1948 paper. And this English sentence has a certain structure and a certain structure of dependency among letters and among words and so on. So the amount of information that you need to allocate to represent the English source could be made smaller than the nominal rate needed to represent the English source. So that is called compression. Okay, see, that's the chapter 5 material. All right, so I will start with this example right here. You can take a look at section 7 of his 1948 paper. Basically, he was interested in finding the entropy rate of an information source, especially English. How much redundancy is there in the source? So he found that redundancy in English is about 50%. 50%. Basically, you can get rid of 50% of information. You will still be able to understand the meaning, or you can still transmit, the compressed version, and then you can still reproduce the original result. So this is my simple example. I have used the alphabet and space, and then where I have on the bar, that means some letters are erased at the position of on the bar. So I and space there is, and some letter erased, and the next letter is A, and another letter erased, and the next letter is T, and there is a space, and there is a erased letter, O, space, erased letter, and so on and so on. So when you take a look at this partially erased sentences, can you make out the meaning of the sentence? What do you think I am trying to say with these partially erased sentence? There are about 13 characters, 13 characters deleted from the original sentence. So here it is about 33% compressed. So there are 40 letters or characters, sorry, and then 13 erased. So 33% has been erased. But can you still make out the meaning of this sentence? So what do you think I am trying to say? Okay, so here is the answer to my example. Basically, the erased letters are W and N, T and G, and so on and so on. So I said that I want to go home and play with my kids. So some of you may have figured out this complete sentence with the partially erased sentence that I have given in previous page. So this is what I mean by compression. Okay, so simple example. Since the English sentence has a structure, temporal structure, and also the frequency of character occurring in sequence. This type of structure allow us to compress a certain amount of information and then still be able to reproduce the complete sentence from the erased version or compressed version losslessly. So that's the motivation for Shannon's work, basically. That is the subject of this part of the module. And we talked about typical sequences. There is a sequence in the typical set, and that typical sequence occurs with this probability, upper bound and lower bounded by this much, right? Whenever you fix epsilon, you can have a large enough n so that this inequality holds, okay? So the probability of sequence must have the following property. Yes, this one. Okay. And then all you need is the entropy of a single alphabet. Okay. All right. And basically AP tells us that for length NIID sequence of random variables, NH bits are good enough for describing the typical sequence. The size of the typical message set is this, and then inverse is the probability of each sequence in the message set occurs. So in an experiment, usually a sequence in the typical set occurs, okay? Shannon has introduced this in his paper, 1948 paper, see page 13. And what we are interested in this chapter, chapter number 4, is the case of English where these characters are dependent with each other, okay? So there is a motivation to consider the entropy rate instead of entropy. Okay, so Shannon's paper, Shannon uses Markov chain to describe English. So one letter to the next one and next one and the next one. In sequence, they have a dependency structure. So Shannon uses Markov chain to describe that dependency structure. So if you click this, I will send you this Shannon's paper in a talk room, and he talks about zero order, first order, second order Markov chain, and the first order word Markov chain, second order word Markov chain, and so on. And he talks about, he gave this quote: can we define a quantity which will measure in some sense how much information is produced by such a process, or better, at what rate information is produced? So entropy rate gives this rate, quantity. So here is the Shannon's example. So, each alphabet symbol is treated independently, treated to be independent. Each letter, each symbol is independent from each other, and they are equiprobable. And then if you generate some sample sequence, it looks like this. Does it look like English? Okay, so that's zero order approximation of English. And then this is a first order approximation. So here again, each symbol is independent with each other, but the frequencies of English text has been taken into account. So O occurs more frequently than Q, which occurs very rarely, and so on and so on. So does it look like English, or better than this for equiprobable approximation? A little better. Okay. Now second order approximation. Diagram structure as in English. So this one is a letter is dependent upon previous letter. So previous letter changes the occurrence of the next letter, the frequency of the next letter. So for example, if we have A, then the next letter could be R, right? Or L, more likely to occur. So that type of dependency on previous letter has been introduced. And does it look better than this? A little better than that. And third order, this one is based on two previous letters. So two previous letters determine the next letter. Okay, so this is a Markov chain based on third order. And then why don't we stop at doing letters? Why don't we use words, right? If you have a word U, then the next letter, next word with the next letter with a high probability will be R, right? U, R, right? Something like that. And using a first order Markov chain, it looks like this. Representing and speedily is good. So this, since it is the unit is word, so it looks more like a looks more like an English. Okay, and now let's do the second order approximation. Second order word approximation. So this is a Markov chain. So the fifth one is let me read. The first order word approximation rather than continued tetragram, n-gram structure, it is easier to better. So here so here words are chosen independently. It's not Markov chain, sorry, but with their appropriate frequencies. So word frequencies are used, but each word are independent. Okay, it does not depend on previous word. But this sixth one depends on previous word, okay? So head depend on previous word, the, and end depend on previous word, head, and so on, okay? So it is a first order Markov chain in terms of word. So this is the examples that Shannon has gave in his 1948 paper. So you can use Markov chain to describe English sentence, English source. So in this case, maybe if it is a character or letter, each one is a letter. If it is a word, then it is a word out of a complete word set. And we can talk about the joint distribution for time, certain time, t. If you translate by time t, the joint distribution of n-tuple and the joint distribution of n-tuple, time translated by t much. If these two are the same, then we say that the stochastic process is stationary, and then Markov chain is a typical one that we have defined already. Given present, the past does not matter in Markov chain, and the Markov chain is time invariant if the transition matrix is time invariant, and the stationary distribution is given as this. And if the initial distribution is equal to the stationary distribution, then the Markov chain is stationary. So that is just the definition of a Markov chain. And this one is the entropy rate Shannon defines. We want to consider a sequence of random variables, okay? X1, X2, Xn. Now these sequence of random variables are not IID anymore, okay? So they are just the sequence of random variables. How does the entropy of a sequence of n random variables grow with the n? That's the question Shannon raised. So let's define the possible entropy. Possible entropy is nothing but entropy of these n random variables divided by n, and let the n goes to infinity. Okay, and that is the possible entropy. Definition of possible entropy, and when it exists, we can use it, okay? So for example, when x1, x2 are IID, is a special case, the rate attains the maximum, which is entropy of one of them, okay? It's a straightforward derivation. When x is independent, but different distribution is just the sum of the entropies of individual ones. So that is a possible entropy, okay? So in this case, we can talk about a page load of words, n words, right? And then we can talk about the entropy of n words, right? Or we can have n letters, and then we can have entropy of n letters in sequence. So that is a per symbol entropy because we have divided by n the number of elements, number of random elements, right? And Shannon also talks about conditional entropy rate. So conditional entropy rate is defined to be h prime x, which is the limit n goes to infinity, conditional entropy of xn given all the previous letters, all the previous random variables, okay? And for a stationary process, entropy rate is equal to per symbol entropy. Both limits exist and equal. That's the statement. We can prove this statement by considering this one, okay? So entropy of xn plus 1 given all the previous one is less than or equal to entropy of xn plus 1 given xn to x, or only up to x2, okay? So this one is larger than this left-hand side. Why is that? Because this is less conditioning. So conditioning reduces entropy. So this one is smaller or equal to the right-hand side. So after you have obtained that, we can invoke stationarity of this stationary process. So we can bring this down to this, okay? So n minus 1 to x1 and xn, because it is stationary, this holds. All right, and then we have this result. Okay, so this one we have one more random variable, right? Xn plus 1. The structure is the same. Okay, so here we have one more random variable, which is xn. So this one and that one is proven to be to have this relation. Inequality goes this way. Okay, so as n grows, this measure right here is getting smaller or at most stays, right? So this is non-increasing, so it never increases, right? It either gets smaller or stays, okay? So we have a sequence of measure or number getting smaller or stays, right? So it's a non-increasing series of non-negative numbers. So this is also non-negative because it's entropy. So we know that it is a non-increasing series of non-negative numbers. Since it is a non-negative number, it is bounded from below, which is 0, right? It is bounded below, which is 0. So it is getting smaller or stays, right? But it is bounded under by 0, so it must converges. Okay. So entropy, conditional entropy rate, because of this property, converges. So the limit h prime x, which is conditional entropy rate, CER, exists. Convergence from above.